I'm Daniel Levine, and this is the Bio Report. Prolific Machines uses light to precisely control virtually any function in any cell to transform what's possible with biomanufacturing. In combination with optogenetics and AI, the technology has the potential to impact a wide range of industries from food production to pharmaceuticals by enabling new capabilities, reducing costs, and improving sustainability. We spoke to Deniz Kent, co-founder and CEO of Prolific Machines, about the company's photomolecular platform technology, the benefits it provides over traditional biomanufacturing, and how it can be used to not just cultivate meat, but make a steak. Deniz, thanks for joining us.
Thanks for having me.
We're going to talk about biomanufacturing, Prolific Machines, and its platform technology, which uses light to control cells and reduce biomanufacturing cost. I understand that company's origins are tied to an experience you had volunteering in a Syrian refugee camp in your hometown of Antioch, Turkey. I'm wondering if you can explain what happened.
It came to me through my mother, actually, who was working with the Danish Refugee Council, which is a charity that was helping Syrians get rehabilitated into Turkey. And there was around 600,000 Syrians came to my hometown. And it was a really difficult problem to solve because my hometown only had 125,000 people. And so trying to integrate everyone is a real challenge. And my mother was putting on these job fairs, trying to connect these refugees with the people who could offer jobs. And I took a break from my PhD and went over and helped her. And it was some of the most rewarding work of my life. And I spent my career, publishing papers and writing patents, and it was all very abstract. But then going into this refugee camp and talking to people, and, we helped, I think, like 30 people get a job, or 35, something like that. So a drop in the ocean, relative to the bigger problem. But it felt really good. It felt like I was doing something meaningful, really truly meaningful for the first time, and being able to see the impact. Also made me very interested in climate refugees because, I don't know, I'm sure you know, the number of refugees that we're going to have because of extreme weather and rising sea levels is going to expand dramatically in the next few decades. Probably is going to be in the hundreds of millions of people, maybe in the billions of people. A lot of humans live by the sea or close to water. And so even if sea levels rise a little bit, that can displace vast quantities of people. So I think it's going to be one of the biggest challenges of our time. It is, in my opinion, the part of climate change that I think is going to be the most disruptive. I think it could lead to a lot of rise of extremist groups, terrorism, nationalism. It's a future that I think is worth avoiding if we can. And I think biomanufacturing has an important role to play in that because biology can make a lot of things. But the proportion of the things that it is currently making relative to the sort of potential of stuff that it could make is actually only sort of playing in a small slither right now.
So make that connection for listeners who may not be well versed in biomanufacturing for industrial and food products. How does this relate to climate change and what might it do to forestall it?
So biomanufacturing is a field where you use cells to make things. And there's many different things that cells can make. They can make You can use fish cells to make fish. You can use cow cells to make beef, chicken cells to make chicken. You can also make a lot of like sort of specialty proteins that you wouldn't necessarily recognize the names of, but are important parts of our food system. So this is stuff like lactoferrin or osteopontin. These are molecules that keep babies healthy in baby formula. In all these cases, currently, these come from animals. And there's a bunch of problems with that. The most important one is the efficiency with which those animals convert calories into the things that we want is quite low. So, for example, cows, for the most part, some cows do graze, and that is a good thing. But a lot of cows are fed soy. And the fact that they're fed soy is not a problem in and of itself. The bigger problem is the amount of soy they need to be fed relative to the amount of products that they make. So, give you an idea, around 30 calories of soy need to be fed into a cow to get 1 calorie of beef. Versus if you're just growing the cow cells directly, which is what biomanufacturing does, you can get this down to about 2.5 calories to 1 calorie out. So talking about like an order of magnitude more efficient in terms of calorie usage, if you grow the products directly without having to go through the intermediary of a sentient animal. And the reason for this is because animals have processes that are energetically expensive. So, for example, if you want to maintain an immune system, which is something every animal has to do, that in and of itself is extremely expensive calorifically. So a lot of we're growing the soy at huge expense, like cutting down our rainforests, and then we're feeding the soy to animals, and most of what we're feeding it doesn't even go into the stuff that we want. Most of it goes into stuff like powering an immune system or powering consciousness. Our brains are extremely energetically intensive. And so these processes you don't have if you're just growing cells in a bioreactor to directly make the products that you want. And so there's a big efficiency gain. There's also, for some products that come from cows, you have the methane advantage because methane is produced not from the cows themselves, but from the bacteria that live in the gut of the cows. And so if you don't have to have the cows, then you don't have to have those bacteria in the gut of the cows, and they don't produce the methane, and the methane is a very potent greenhouse gas. So if you just grow cow cells in bioreactors, it will produce zero methane because there's no bacteria. So there's many different reasons why, from a climate perspective, this is a good idea. There's also various non-climate arguments for why this is a good idea, ranging from animal rights issues to zoonotic diseases, which are diseases that come to us from animals, to land use and water use. The list just goes on and on and on and on.
Prolific Machines has developed a photomolecular biomanufacturing platform. What is that, and how does it work?
So what Prolific is a new infrastructure layer to control biology using light instead of molecules, which is typically how biology is controlled. What I mean by molecules is stuff like chemicals and proteins that you add into the soup that the cells grow in, and those chemicals and proteins tell the cells what to do. So we use light to tell the cells what to do instead of those molecules. Now, this has a number of advantages. One is that light's the cheapest possible input into biology, so this is the floor for how cheap biomanufacturing can ever be for any application. Light is also extremely tunable, so you can precisely control where you shine it and when you shine it. The where you shine it allows you to create patterns, which makes never before possible products. And the when you shine it gives you yield advantages. It's also sterile, it's highly reproducible, and it's amenable to this closed loop optimization where you can basically teach machines how to control biology. So there's 3 parts to this. One part is we build genetic tools, and those genetic tools
allow you to control any pathway inside of any cell using light. So the way that this works is that we attach light-sensitive proteins to various targets inside the cell genetically, and then you can toggle those targets on and off by shining different colors of light on the cells. We also build hardware that is plug and play with existing biomanufacturing infrastructure, and we build an algorithm which has an embedded understanding of transcription, translation, protein degradation, all of these things that are important for biology, and takes all of the sensor data from the bioreactor and makes predictions with its embedded understanding on what is the best light pattern to apply to get to your set point. And the set point could be whatever you want. It could be, more antibody, more vaccine, more beef, more lactoferrin, whatever biological product you are optimizing for. This algorithm can predict what the right light patterns will be to get you there.
So you're actually engineering the cells to be responsive to the light.
Correct, yeah.
Does it matter the frequency of light? Is it visible light? Is it different frequencies do different things?
Excellent question. It's visible light. So different colors of light do different things. It depends on which light-sensitive proteins you use. So these light-sensitive proteins, they all come from nature. So originally evolved in bacteria. They're in all plants. They're in all algae. So we eat them all the time. If you ever eat a salad, you eat a bunch of light-sensitive proteins. Of course, they all just get degraded into amino acids once we eat them or cook them. But different light-sensitive proteins evolved in different contexts. They're the sensory mechanisms of plants and bacteria and algae. So I don't know if you have a plant at home, but you notice your plant starts growing towards the window. Have you ever noticed that?
Yeah, of course.
So how does the plant know where the window is? Because it doesn't have our eyes. It doesn't have any of our sensory equipment. The way that it knows it is because it has these light-sensitive proteins that change shape when the light hits them. And it uses that to orient itself towards the light. So if you get rid of these proteins in plants, the plants just grow randomly. It's very interesting. So anyway, we can take these proteins and put them, which we know are safe, and we can put them into cells that don't normally have these proteins and tether them to things that we want to control with light. So this could be receptors on the surface of cells, enzymes, transcriptional activators, anything, any protein.
What are the range of cellular processes that you're actually able to control with light?
So I can give you an idea of some of the stuff that we're working on. So the first tool that we built was called optoreceptor. So this is a way to activate cell surface receptors using light. So this eliminates the need for growth factors, but it also increases the rate at which the cells can grow. So it makes them faster. The second tool that we built is called optodiff. This is a way to turn one type of cell into another type of cell using light. So you can do this just in bulk, or you can also do this to create patterns. So this is going to be key if you want to make a structured product, which could be, in the food space. It could be, a Wagyu steak or a bluefin tuna steak. But in the therapeutic space, you can use this to make higher fidelity representations of disease models. You can use this eventually to make human tissues for transplantation. Then we started building tools to control transcription, which is basically the conversion of DNA into RNA. So you can do that with light. You can control the rate of that. Building tools now to control metabolism using light, building tools to control the secretory capacity of the cell using light for biopharmaceutical applications. So there's a lot that you can do here because it's a very flexible toolkit where any protein inside the cell can be targeted with these light-sensitive proteins.
And you touched on this, but what are the benefits of using light to control cellular function, and how does this differ from more traditional biomanufacturing processes?
Yeah, so light is, like I alluded to before, the cheapest and most controllable way to manipulate biology, because light is just electricity going into an LED. Electricity is being commoditized by the consumer electronics industry. LEDs have been commoditized by the consumer electronics industry. And electricity is being commoditized by civilization. And so electricity is a very, very good input into biomanufacturing. And it's obviously because you can control when you shine the light and where you shine the light, which are things that you can't do with molecular inputs. The traditional inputs are like dropping a drop of cream into a cup of coffee and then watching the cream dissolve. You can't really control where the cream goes once you've dropped it into your coffee. And so this is the issue that we have with biomanufacturing right now, is that we have these inputs that we add in and then we hope for the best. Whereas what Prolific is doing is building these reactors where you don't just add something in and hope for the best. You monitor and you dynamically adjust the light patterns to get to your set point. And it's not you add it in and hope for the best. It's you're adding something in and constantly monitoring and tuning. And so it's a bit like going from a car that you need to drive yourself to a car that starts driving itself.
You're also using machine learning as part of your platform. How does machine learning enhance or enable what you're doing? And does it allow the technology to react to what is taking place in the cell in real time to improve the precision of the process?
So the sort of software part of this that I was alluding to is machine learning, in the sense that you can train a model to predict what the best light pattern will be given all of the data that it's generated in the past on trying light patterns and getting certain results. So we have been generating lots of optogenetics data on many different tools. And you can use all of that data to train an algorithm to start learning what the right light patterns will be. And these algorithms will get better and better over time. As you get more data, more people using this, you get a larger pool of data to train your algorithm with. And then the better those algorithms get, the better the performance gets, which leads to more people using it, which leads to more data, which leads to better light patterns, which leads to better performance, which leads to even more people using it. So that's basically what we're doing.
Does this technology integrate with existing manufacturing capacity, or does it require designing a facility from the ground up to use it?
It integrates with existing manufacturing capacity. So the constructs can be put into the existing cell lines. The hardware is plug and play with existing bioreactors. The software basically just lives in the hardware that we provide.
And how exacting and reproducible is this as a method of manufacturing?
It's the most reproducible method of manufacturing. And the reason for that is because traditional biomanufacturing relies on recombinant proteins to control the cells. And those recombinant proteins have a huge amount of batch-to-batch variation. So, talk to any scientist. And, I have a lot of trauma on this from my past life as a scientist. If you buy the same recombinant proteins and you use them in the same cell line, same protocol, you don't always get the same result. And I've lived this several times, and I call up the recombinant protein companies, and you're like, well, I bought the same thing. I'm not getting the same result. So what's up with that? And what they'll tell you, and you can try and call them up and do this experiment yourself. What they'll tell you is, we have batch-to-batch variability. We're sorry about that. We know that it exists. There's not much we can do about it. And the reason why they have it is because these proteins are made from biological systems which are not static. And so these are traditionally genetically engineered microbes that make these recombinant proteins. And those can change. And so the output can also change. And there's two ways that you can deal with this. Neither of them are particularly good. One is the sort of YOLO approach to biomanufacturing, where you say, okay, we know that these inputs are not super reproducible, but we're just going to add them in and hope for the best. And sometimes it will work, and sometimes it won't. The other thing to do, which is what the responsible companies do, you have a big quality control team that has to test every single batch of new proteins that come in to make sure that they work. And that works, but now you have to have a whole team of people where their only job is just making sure that these inputs work. With light, 450 nanometer wavelength light today is exactly the same as it will be tomorrow, and it's exactly the same tomorrow as it will be 1,000 years from now. And so we've never had inputs into biology that are as reproducible as light is. And so I think that reason alone is enough of a reason to switch to it. But then there's all of these ancillary benefits like yield advantages, cost advantages, being able to make things that nobody else can make on the food side and on the drug side.
Is there any way to quantify at this point the time and cost benefits of this approach?
It very much depends on what you're using it for. So, for example, if you are using this to make a nutritional protein that can't otherwise be made, or a therapeutic protein that can't otherwise be made, then you're kind of comparing against something that's impossible, right? So it's an infinite advantage because you're turning something from impossible to possible. And then there are other fields where it's more of an incremental benefit, right? Depending on which tools you're using. Let's say, you want to make your biosimilars cheaper, or you want to make your cultured meat cheaper. You share in the cultured meat space. The biggest cost driver is the media, which is the soup that the cells grow in. And inside that media, the biggest cost driver are these recombinant proteins that you have to add to tell the cells what to do. So it's around 90% of the media cost, the media cost is around 80% of the total cost. So Prolific can eliminate those recombinant proteins entirely using light. So to give you an idea of, it's a very, very large proportion of the total cost stack.
An early focus of the company has been cultivated meat. Is that because that market is more sensitive to cost than something like high-value biotherapeutics?
Yeah. Well, it was mainly because I love eating meat and feel terrible about it, and so I wanted to do something about that. But the meat industry is very sensitive to cost for sure. And I was basically convinced that there was a huge commercial opportunity with cultured meat, but it was never going to work with the existing toolkit. That you needed to have better tools, and specifically you needed to grow meat with light in order to make that commercial opportunity a reality. So that's kind of the road that we started heading down. And then we realized that the tools that we were building for that had so many different applications, and people were very interested in paying us for those early applications that required much smaller volumes. Because the issue with meat is that there's a really big prize, but you have to get to quite large reactor sizes before you can realize that prize. Whereas with pharmaceuticals, or even with these higher value nutritional proteins, you don't need to get to crazy big reactor volumes to have profitable production. And so that's why we are focusing on the pharmaceutical industry and the sort of high value nutritional protein industry as starting points, because we can address them now, and we can get to profitability in the short term in those markets. And then the technology will continue to build momentum, and then eventually it will get deployed in cultured meat and many other places. I kind of see Prolific as this evergreen optogenetics asset where, we will continue to innovate on controlling cells with biology, and then there will be many different offshoots from that. An offshoot to help make meat, an offshoot to make baby formula, an offshoot for biosimilars, an offshoot for difficult to produce therapeutics.
To what extent has costs constrained the growth of the market for cultivated meat today?
It's the biggest problem. The other problems in cultured meat have largely been addressed. Like, we know that it can get regulatorily approved. We know that people like the taste. We know that it's nutritious. We know that it's safe. Cost remains the issue to solve.
And is there some reduction in cost that needs to be achieved to make it a large and viable market?
In my opinion, the turning point existing tools will and already do have cultured meat on the market, but it's going to be super expensive niche products. In my opinion, the tipping point for cultured meat will be when you can produce meat that is cheaper than factory farming. And I think the only way to do that will be using Prolific's technology. We want to make it available to all meat companies and to all cultured meat companies.
One of the challenges with biomanufacturing food and industrial products is the volume that's required. You talked about needing much larger bioreactors. These are bioreactors that are magnitudes larger than what's used for medicines. And scalability has been a big challenge with this. As you get to a larger bioreactor, the material inside may act differently. How scalable is this technology?
So just to give you an idea, the pilot facility that Prolific currently has and we've built goes up to 200 liters, which is full commercial scale for pharmaceutical applications. Meat becomes profitable at around 20,000 liters with our technology. And with our technology, that gets you to about 40 to 60% gross margins, which are, unheard of in the meat industry. The scalability of light is quite easy. It's good in the sense that you can measure light. Like you can measure how it passes through cells, and you can measure how it passes through the soup, the media. And so you can build those measurements you can use those measurements to build models. And those models can be used to predict how much this will scale. And the degree to which light passes through cells is dependent on many things. It's dependent on the density of the cells, the color of the light that you're applying. But several people have modeled this, us and others, and we don't think that the scaling is going to be an issue up until about 100,000 liters. At 100,000 liters, we think that you'll be able to illuminate it, but you're going to need to be a little bit more creative about how you do it. Once you want to go above those volumes, you're going to have probably some internal illuminators as well as external illuminators. We're getting a little bit into the weeds here. I don't know how far down this rabbit hole you want to go, but the short answer to your question is up to 100,000 liters, we don't think it's going to be an issue. And above 100,000 liters, we have a number of solutions for how we think we would do it. But above 100,000 liters is only required for precision fermentation, which is the field of using microbes to make things. And it is a field where Prolific's technology could work and would be useful, but it's not a field that we're getting into in the short term because we're focusing on mammalian cells, and mammalian cells make all of the highest value products.
You kind of alluded to something in passing, but I think if most people think of cultivated meat today, they think of a product that's like ground beef. You indicated that you could actually make a steak with this technology. Is that correct?
That's correct.
If you can make a steak, how big a leap is it to go from that to a lab-grown organ? Is that something you eventually see using this technology to produce?
I do, yeah. It's fundamentally the same technology that you need to do for both. If you want to make something for food, it is easier. The reason why is because at the end, it doesn't need to be alive or functional. It just needs to be tasty and nutritious. So if you want to do this for human tissue, it is absolutely possible. In fact, we have already shown that we can control human cells with light. But food is technically easier, but both are possible.
And what are the regulatory hurdles for using this technology?
Well, it depends on what you're trying to make. So if you are trying to make a drug, you have to go through clinical trials, like any new drug. If you're making a biosimilar, you have to do the equivalence trials to the drug that's already been approved. If you're making a food, it depends on what you are making. So, for example, if you're making bovine lactoferrin in bovine cells, and that is the same as what the cows are making, then you don't have to, the burden of proof is lower than if you are making, say, human lactoferrin, which is not currently being eaten, apart from by babies, in breast milk. So it seems like a simple question, but it's not a simple question because it depends a lot on what product you are trying to make.
Beyond cultivated meat, where do you see the big early opportunities to apply this technology?
I think it's in the pharmaceutical industry.
And is it going to be on biosimilars or anywhere?
I think it's going to be every part of the pharmaceutical industry where mammalian cells are making a high-value therapeutic product. So that could be biosimilars, that could be production of difficult-to-produce therapeutic proteins. Even in gene therapy manufacturing, I think there's an interesting opportunity. There's several.
And in those cases, would it be control rather than cost that's the biggest benefit?
It's both. control and cost.
How do you ultimately envision your platform changing the landscape of biomanufacturing? Do you see it enabling new types of production or making any products commercially viable that may not have previously been so?
Yes, all of the above. I mean, I ultimately see Prolific as this evergreen optogenetics asset that just continues to do innovation on how best to control cells with light. And then there's many different pathways that kind of stem from that commercialize that technology. So, one is meat, one is baby formula, another is these, biosimilars, the difficult to produce drugs. There's many different ways to commercialize this. And that could be, sprouts from a single company, or it could be spin-outs. That's still to be determined, but there's a huge opportunity in using biology to make things. And I think Prolific is very well situated to do that.
And what's the business model? Do you expect to use the technology to produce products of your own, or are you pursuing collaborations and licensing the technology, or applying a service model?
Right now, we're going down the partnerships route. So we are partnering with people who want to use biology to make things, and we are allowing them to make those things cheaper, better, or some of those things that are just currently impossible to make that we're not allowing them to make, full stop.
Have you disclosed any of those partnerships yet?
We have disclosed some, but not all. I have my PR person on the line, so she'll tell me not to tell you anything.
We can knock her off if you like. The company has raised a little more than $85 million to date. How far will that take you?
So we just closed our Series B. The purpose of the Series B was to scale the technology to 200 liters and to generate commercial traction, which is what we're going to be able to do between now and, let's say, 2027. And then we'll probably do one more funding round to take us to profitability.
Deniz Kent, CEO and co-founder of Prolific Machines. Deniz, thanks so much for your time today.
Thanks for having me. I'll just end by saying that if you want to work with us, feel free to email us at partners@prolific-machines.com. Or if you want to work with us in any way, my email is also dennis@prolific-machines.com. Hey, don't be afraid to reach out.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send an email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.